Hello and good morning friends, a video course in advanced hydrology. We started the new chapter in the last class on atmospheric water. We looked at the concept or certain properties of the water vapor in the atmosphere. Then we said that you will look at the atmospheric circulation topic on your own as a reading assignment. We also looked at the vapor transport, the Reynolds transport theorem, various properties or various variables that are involved in that, and how we can apply that to a multi-phase problem. We will come to that little later. Then we looked at various interrelationships or various equations which give you the relationship between different parameters such as the vapor pressure, the atmospheric pressure, the relative humidity and so on. Right. Towards the end we define what is the saturation vapor pressure, the vapor pressure, the relative humidity, and then we started looking at finding out the water vapor in a static atmospheric column. Okay. So, if we look here, we drew this figure as you can see here. So, we consider this cylindrical element, all right, of a atmospheric column, a cylinder basically, and our focus of attention will be between two cross sections, that is 1 and 2. Okay. And we are trying to find out how the pressure will vary as a function of height and also how the temperature would vary as a function of height. Okay. To be able to find out the atmospheric water vapor in the static column, we said that we are going to use these two basic laws, okay, which will govern the properties of water vapor. One of them was the ideal gas law, which we said is pressure is equal to rho R T from the ideal gas law, that is, this was 3.2.12, and then we said another thing we are going to use will be the hydrostatic pressure law, all right, which is dP is equal to negative rho A G dz in this particular case. So, let us get started today and then look at how we can do that. All right. The first thing we will do is that as we go up into the atmosphere, the temperature changes, all right, and the variation of air temperature in the atmosphere, as you all know, as we go up the temperature decreases, all right, with altitude or height can be given by this equation. That is dt over dz is equal to negative alpha, and I am going to number this equation as 3.2.14, okay, where what is alpha? Alpha is what is called the lapse rate. Okay. So, alpha is the lapse rate. Okay. Normally, it is expressed in degrees centigrade per kilometer of height, and its value is between 6 and 7 and depends upon the climatic conditions and so on. Okay. So, lapse rate is the rate at which the temperature lapses as we go up, all right, and this is 3.2.14. Now, what we will do is we will do certain algebraic manipulations and then try to find out the variation of pressure and temperature as a function of height. So, if we take equation 3 to 12, all right, it will give me rho as P over R A T. Remember what was 3 to 12? It was nothing but the ideal gas law, and ideal gas law states what? P is equal to rho R T, right. So, from P is equal to rho R T, I have just written down the expression for the density rho A, and then we put this into equation 3 to 13. And what is 3 to 13? If you go back, it is this equation, which is the hydrostatic pressure law. So, what we are doing is basically we are combining these two equations. Okay. All right. So, if you did that, this is what you will get: dP over dz is equal to negative of your Pg over Ra T. Okay. Or if you separate the variables so that we can integrate, what we have is dP over P is equal to negative g over RAT of your dz. All right. I have slightly rearranged this equation on the left hand side. Okay. Now, I want to replace this dz in the form of dt, okay, and there is a relationship between z and t, that is how the temperature changes as a function of height. Okay. So, if you do that, if you look at equation 3, 2, 1, 4, you have dz is equal to negative dt over alpha. All right. What is 3 to 14? It is the lapse rate. This is all right. So, dt dz is this. So, dz will be dt over alpha with a negative sign. Okay. That is what we have done here. Okay. So, now what we do is we put the value of dz from here into this, okay, and what you will then get is dp over p is equal to minus minus will cancel out. You will have g over alpha r a as a constant and then dt over t. Okay. Now, you can see that you have the variables on either side which you can integrate, which are the climatic variables. So, integrate on both sides. What are we going to get? And when we are integrating, let us say between locations 1 and 2. Okay. Remember what is locations 1 and 2? We have defined the height z1 as 1 and z2 as 2. Okay. So, if you did that, you will have natural log and p2 over p1. This will be natural log of p taken between p1 and p2 or 1 and 2. So, that will be natural log of p2 over p1. G over alpha r a is constant. So, that will remain outside, and when you will integrate dt over t, it will be natural log of same thing, it will be t2 over t1. Okay. And then you make slight readjustments, which will give you p2 as p1 times t2 over t1 raised to the power g over alpha r a. Okay. So, this is your relationship between p2 and other things, and I am going to number this as 3.2.15. all right. So, this way we are able to write the expression in which we can calculate the pressure at any height from the ground. Okay. And what do we need to know? We need to know the pressure on the ground, that is P1, and the temperature on the ground T1, and also T2. T2 is the temperature at the same height, all right, which we would be able to know given the lapse rate equation to us. All right. So, how do we do that? So, let me take the lapse rate equation, which is dt over dz is equal to minus alpha. All right. What is dt over dz? If you write it between 1 and 2, it will be T2 minus T1 over Z2 minus Z1. From your basic knowledge of your calculus, you will have negative alpha, right. So, what does that give you in terms of T2? T2 is nothing but your T1, the temperature on the ground, minus your lapse rate times the difference in the heights, which is Z2 minus Z1. Okay. And let us say then that this is your 3.2.16. Okay. So, 3.2.16 will give you the variation of temperature as a function of height, and we have already derived the equation or looked at the equation for 3.2.15, which is giving you the variation of pressure as a function of height. So, with that, what we are going to do is we will look at an example, but before I do that, let me go back to my figure and see or try to plot how it will look like. Okay. Here it is. So, we have considered this atmospheric column, all right. The height is Z2 minus Z1, Okay. So, let us first plot the temperature. All right. Temperature, as you have seen, it decreases as we go up. All right. T2 is equal to T1 minus alpha and delta Z. Right. So, if you did that, how will it look like? Is the equation linear or non-linear? It is obviously a linear equation. All right, and it will be sloping downwards. All right, because it is decreasing as we go up. Okay. So, it would simply be something like this. Okay. So, if the temperature here is, this is Z1, this is T1, at your Z2, this would be your T2. Okay. So, as we go up, the temperature decreases, and the slope of this line, as you see, would be what? This would be your lapse rate, which is alpha. Okay. The slope of this line is nothing but the alpha. So, it is just an equation of a straight line. What about the pressure? Pressure is, as we have found out, it is a non-linear relationship. Here it is. Okay. Pressure decreases non-linearly as we go up. All right. So, it is a equation. If you plot it, it will look something like this. Okay. Where this is your, at height Z1 you have the pressure P1, which is close to atmospheric at height 1, and then at Z2 this is approximately P2. Okay. So, that way we are able to plot the both temperature and pressure variations as a function of height. Now, why we are doing all this is important in calculating or estimating the amount of precipitable water in an atmospheric column. Okay. What we will do is we will look at an example which will try to demonstrate this. Okay. So, we take an example in this chapter, which is our first example here, which says that calculate the vapor pressure which is E, air pressure which is simply P, comma, relative humidity which is, we are going to denote this as RH, and air density at an elevation of 1500 meters. All right. So, which is about 1.5 kilometers into the atmosphere. If your P is equal to 101.0 kilopascals. All right. These are the data which are given on the ground, the air temperature. Capital T is equal to 25 degree centigrade, and the dew point temperature and we will denote this as T subscript D is equal to 20 degree centigrade on the ground. Okay. So, the climatic data on the ground are given, and what you have to find is what will be the vapor pressure, the air pressure, relative humidity and the air density at a height of 1.5 kilometers. Okay. You will obviously need some more data in this. So, the other things that are given is assume a lapse rate of 9 degrees per kilometers, all right, which is constant or same, which can be assumed for both T and T d. Okay. So, this is the assumption, this is T d. All right. So, air temperature and the dew point temperature, for both you can take the same lapse rate, which may not be the case ideally, but for this example purposes we take them to be same. And the gas constant R A, which would be needed is equal to, is given to you as 287 joules per kilogram degree Kelvin, okay, which is constant as a function of height. Okay. What does that mean? That last sentence, it is constant as a function of height, means that you have to ignore the variation of R A as we are going up. Okay. So, just use this value 287. Ideally, it will be changing as the humidity level will be changing. Remember, there is a relationship between R A and R D, which is related with UV, but we are to ignore that. Okay. Okay. So, moving on, we look at the solution of this. Okay. It is a good habit, as I have said earlier, that to summarize all the data that are given to us. Okay. So, let me first write everything which is given in one place, so that you can refer to this small corner in your notebook if you need any data. Your Z2 is 1500 meters, Z1 of course is 0, you can take on the ground. Pressure that is given is 101.0 kilopascals. T1 on the ground is 25 degree centigrade, and TD on the ground is given as 20 degree centigrade. Also given to us is the alpha as 9 degree centigrade per kilometers. R A is 287 joules per kg. Okay. And alpha is same for both T and TD. So, what you have to find is the vapor pressure at height 2, what is the P2, the air pressure at height 2, what is the relative humidity at height 1500 meters, and what is the air density at height 1500 meters. So, these are the 4 things we have to find. Okay. So, we will work on these in that order. So, first we will look at the vapor pressure. How do we find the vapor pressure at a height of 1500 meters? Okay. If you remember the concept of saturation vapor pressure, there is an expression that is given to us, E2 is equal to 611 exponential and so on. We can put the value of air temperature in that, and it will give you the saturation vapor pressure. But an very important aspect is that, because the vapor pressure gives you an indication of the relative humidity or the moisture content, right. So, what we can do is we can substitute the dew point temperature in that expression to get the vapor pressure instead of the saturation vapor pressure. Okay. This comes from the definition of the dew point temperature, which we had seen earlier. Okay. So, what we can then do is, you can write, we can calculate E2 at the height 2, which is 1500 meters in this case, as 611 e to the power this whole expression, which you should have in your notes. This is TD at height 2. I am using another superscript now, so do not get confused. It is the dew point temperature we are talking about. Okay. Now, what we have is dew point temperature on the ground, but we do not have the dew point temperature at height 2 or 1500 meters. But what is given to us is that the dew point temperature also follows the lapse rate, the same lapse rate. So, using that we can find out what will be the TD2. Okay. So, let us do that. Your temperature, dew point temperature at height 2 would be temperature at 1, right, minus alpha times of your Z2 minus Z1. Okay. Now, TD1 is given to us as 20 degree centigrade, minus you have 9 degree centigrade per kilometer as your lapse rate, times Z2 minus Z1 is 1500 meters, but our lapse rate is degree centigrade per kilometer. So, we put the value of Z2 minus Z1 in kilometers. So, that kilometers will cancel out. Okay. you have to be careful while choosing the units or putting the units into a particular equation. Okay. You can simplify this and it will give me Td at height 2 as 6.5 degree centigrade. Okay, so now how can we find the vapor pressure? Well, we already have the equation. So, we put this value of, let us say, this T2d into this equation, okay, and we should be able to find the vapor pressure at height 2, right. So, if you did that, you have E2 as 611 e to the power of, you have 17.27 times 6.5. Remember, in this equation we will put the temperature in degrees centigrade. Okay. If we do that, the E2 will come out in pascals. It will be 237.3 plus 6.5. It is in degrees centigrade. So, once you simplify that or calculate, it will be 968.3 pascals. So, your one of the quantities which you have to find is that vapor pressure at a height of 1.5 kilometers is 968.3 of your pascals. So, that is your one of the answers. Okay. So, let us move on and then we try to find out what will be the atmospheric pressure P2 at a height of 1500 kilometers, sorry 1500 meters, right. We have just derived an equation which relates P2 with P1 and temperature, all right. So, let me first write it down. You have natural log of P2 over P1 is equal to G over alpha R A natural log of T2 over T1, okay. And that we had seen that is going to give you P2 is equal to P1 times T2 over T1 of raised to the power G over alpha R A. Okay. Now, if you see the right hand side, we know P1, we know T1, G is the constant, acceleration due to gravity, alpha is known, R A is known. Okay. Only thing unknown is the temperature at a height of 1.5 kilometers, okay, which we can find out using the lapse rate again. Okay. So, you find out the air temperature at a height of 1500 meters as this minus alpha times Z2 minus Z1, same thing which we did earlier. So, this is 25 degree centigrade minus 9 times 1.5, it will be 11.5 degree centigrade. Okay. So, that your T2 is equal to 11.5 degree centigrade. Okay. So, we put this back into this equation. So, that your P2 will be 101.0 times this is P1 in kilopascals, okay, remember that, and then you have T2 over T1, all right, this expression. Okay. Remember, in this equation T2 and T1 are in degrees Kelvin. Okay. So, we have to be careful while choosing the units. So, you have 273 plus T2 is 11.5 which we have just found out, divided by 273 plus what is it, T1, and T1 is the temperature, air temperature on the ground, which is given to us as 25. All right. So, this is degree centigrade, you have added 273. So, that the overall result is in degrees Kelvin. Now, all of this is raised to the power of 9.81 is the acceleration due to gravity, and then you have alpha. Alpha is 9 degree centigrade per kilometer. All right. You have to be extremely careful in choosing the units now. It is per kilometer, but this is an equation in the SI units which will require that your distances are in meters. Okay. So, you have 9 into 10 to the power minus 3 is your alpha, which is degrees centigrade per meter. Okay. And then you have 287 is your RA in SI units. Okay. So, please make a note of this, and I have seen many students committing a mistake, they just put the value of 9 here. So, if you calculate this, it will be approximately 84.6943 kilopascals. Why is it in kilopascals? Because this P1 is in kilopascals. You could have converted into pascals by multiplying by 10 to the power 3, and the answer would be same in pascals. All right. So, this comes out in kilopascals. So, therefore, the pressure, atmospheric pressure at a height of 1.5 kilometer comes out to be about 84.7 kilopascals. Okay. So, you see that the pressure decreases quite rapidly as we go up. Okay. That is why this trekking and mountaineering people, as they are going up, because the pressure reduces, the amount of oxygen reduces as we go up. So, they carry their oxygen cylinders etc., and enough supply with them. Okay. So, this is the next answer. Okay. The next thing we have to find is what is the relative humidity at a height of 1500 meters. Okay. So, you have relative humidity. Okay. And you know that this is given as simply E over E sat or E saturation at a height of 2, okay, or at 1500 kilometers. Now, we have already found out E2 earlier, and what we need is E sat at a height of 1500 meters. What is E sat 2? Okay. So, what will be the saturation vapor pressure at second cross section or at a height of 1.5 kilometers? Well, we know what will be the air temperature at that height. Okay. So, once we know the air temperature, we can always find, we can put the value of that temperature in the expression we have. All right. So, if you did that, you have 611 exponential 17.27 times the air temperature at that height, which is 11.5. Okay. Here it is, we had just found out. This whole thing divided by 237.3 plus 11.5. Okay. And if you solve it, it will come out to be 1357.4. Okay. And what will be the units? Well, it will be pascals. Okay. So, moving on, you have relative humidity at a height of cross section 2 or 1.5 kilometers is equal to your E2 over E2 saturation, which is this we had found out. What is E2? E2, if you go back, is okay. So, 968.3. Okay. All right. So, it is 968.3, and the saturation vapor pressure at a height of 1500 meters we just found out is 1357.4, and it will be 0.7133. All right. So, that implies your relative humidity at a height of 1.5 kilometers is 0.7133, or in percentage you can express this as 71.3%. Okay. So, you see that all these equations which we have looked at yesterday, they are extremely important in finding out the values of humidities and pressures and temperatures and all those climatic conditions at any height, which becomes very important in climate modeling. Okay. All right. So, the next thing we have to find out is, in this problem, what is the density of the air at that height, okay, which is also an important parameters. Okay. rho A 2, how can we find it? Well, we can use the ideal gas law, which is valid everywhere, at the ground or at any height, right, does not matter. Okay. So, P is equal to rho R T, that will give you rho is equal to P at the same location divided by R A times T at the same location is T 2. Okay. We have already found T 2, we have already found P 2, and what is given to us in this problem is that the gas constant R A is constant as a function of height. Okay. So, we put that value 287 and we should be able to get what will be the air density. So, it will be 84.7 10 to the power 3. What is, why I am doing this 10 to the power 3? P 2 is the pressure in pascals, all right, and what we found out was 84.7 kilopascals, all right. So, that is why I have multiplied, so that this is in SI units. So, you have 287 times T 2 in this equation is in Kelvin is 273 plus 11.5 was the temperature at a height of 1.5 kilometers we found out. So, that your rho A at 2 will be 1.03733 kilograms per meter cube. Okay. Okay. So, that ends the solution of this problem, wherein we saw that knowing the climatic conditions in terms of temperature, pressure, humidity, etc., on the ground in terms of dew point temperature, we can find out how all of these things will vary as a function of height. Okay. And once we have done that, we will move on to a very important concept. Okay. Remember that we are still in the phase, or what we are considering right now is the static atmospheric column. Things are not moving right now. Okay. Movement of the moisture we will model later, all right. So, the next thing we are going to look at is how much is the precipitable water in a static atmospheric column, which is a very important concept. Okay. So, let us move on and look at the precipitable water. Okay. In this atmospheric column. Okay. The amount of moisture in an atmospheric column which we had just considered like a cylindrical column is called the precipitable water. Okay. Okay. The amount of moisture which is available in an atmospheric column is called the precipitable water. Okay. The water that can precipitate as rainfall or any other different forms. Okay. How can we calculate this? Calculation of the capacity of this water in a cloud or in a column is very important, okay, because what will come out of that cloud, then we can model that everything will be coming out of this precipitable water. Okay. So, what we do is we consider an element of height dz like we had done earlier, all right, in a column of cross sectional area A. Okay. So, it is the same thing. If you go back, well, let me do not have to go back on that figure. So, it is a cylinder, the cross sectional area is A and its total height is Z2 minus Z1, but we are considering a small strip of height dz. Okay. So, first we will write the amount of water in that strip dz and then we can integrate between the limits Z1 and Z2. Okay. All right. So, what will be the mass of the air what will be the mass of air in the strip of height dz in that atmospheric column. Okay. The mass of air would be what? The volume of that particular element multiplied by the density of air, right. Density multiplied by the volume is the mass, right. So, what is the volume? Area is A, height is dz. So, that is your volume, okay, volume of that strip, and if you multiply it by the density of the air, that will be the mass of the air. Okay. Once we have the mass of the air, what will be the mass of water or moisture in that column? Okay. It is very interesting and very simple concept. So, it would be rho A dz. What do you multiply this by? Okay. If you multiply this by the specific humidity QV, what is QV? QV is nothing but the measure of amount of moisture in an atmospheric column, right. That is how we had defined, all right. So, this is the total mass in the volume A dz. So, it will be equal to, if you multiply this by QV. Okay. So, this gives you the mass of water in a small strip. So, if you want to find out what will be the total mass of water in a height between Z1 and Z2 of an atmospheric column, what do you do? Well, integrate total mass of precipitable water okay, and then if you denote that by m subscript p, it will be the integral of this quantity here between the limits of Z1 and Z2 of your same thing QV rho A dz. Okay. So, this is your small little expression for finding out the amount of water or the precipitable water in a static atmospheric column. Now, how do we actually calculate this precipitable water? What we do is we discretize our whole space domain, all right, and then we work with the average quantities, all right. So, if we actually do it, this is how we in fact work it out. So, if you take small strip dz, we had seen earlier, all right, or delta z for that matter, because we are working with the discrete quantities now. So, let me write this as delta MP in a small strip dz will be equal to what? Okay. It has certain height, let us say small z1, small z2. So, what we do is we take the average quantities. The QV is varying as a function of height. So, we take the bar represents the average quantity of the specific humidity. Similarly, we take rho A bar, which is the average density between those two heights, okay, and then A times delta z is the volume, all right. This we say is then equation 3.2.18. So, what we do is we find out the average specific humidity between any two heights, we find out the average density and then multiply by the area. That will give you the incremental amount of water in that increment, all right, and then we keep on doing it for every 100 meters or every 10 meters depending upon the accuracy desired for 1 kilometers, 2 kilometers and so on. So, what I will do is I will just like to demonstrate how you can actually do that. So, before I did that, let me define your QV bar is the average specific humidity in a column of height delta z, okay. Any suitable delta z we can take, and rho A bar is the average air density average air density of moist air, okay, in a column of height delta z, same thing, okay, right. So, how do we actually do it? Well, this is the expression we have. What is QV bar? Okay. Let us say you have two cross section, delta Z is represented by 1 and 2. Okay. So, average is what we are doing basically, there is a non-linear function you are trying to linearize, all right. So, it is like interpolation. So, you are saying it is nothing but the average of the values QV1 and QV2 divided by 2. Okay. So, any between the delta Z you take the value of QV1 and QV2 and take the average. Similarly, your rho A bar will be rho A1 and rho A2 over 2. Now, how do we find this QV1, QV2, rho A1 and rho A2? Okay. We have already solved an example in which we have seen how we can do some of these things. For example, let us say rho A1. We know that your rho A is given by P over RAT, ideal gas law, all right. This will give you rho A1 as P1 over RAT1 and rho A2 as P2 over RAT2. Okay. So, ideal gas law is applicable at all the heights, right. So, all we are doing is we are finding out the density of the moist air at different heights. Okay. How we can do that? We know the pressure and temperature on the ground, we know the ideal gas constant, and then we can find out what will be P2 and T2. We just looked at an example in which we calculated the temperature and pressure as a function of height. Okay. This RA in that example was constant, but to be more accurate we can allow the variation of that, all right, and then use slightly more accurate values, all right. But for all practical purposes, if we can keep that constant, that should be fine. So, you know how to calculate then rho A1 and rho A2, we can keep doing that and we can find out what will be the average air density. Similarly, your QV is given by 0.622, this expression we had looked at yesterday, E by P, right. So, that will give you your QV1 is equal to 0.622 E1 over P1, okay, which is basically at height Z1 or at cross section 1, okay, and your QV2 would be 0.622 E2 over P2, which would be at height or cross section 2. Okay. Now, there are a few more things which you would need to calculate, that is your P2 and T2, for which we already have T2 by the lapse rate. I am not going to write the equation again, all right, and P2 by the equation derived earlier. Okay. And also this E1 and E2, we use dew point temperature as at those heights, and if we need to calculate E saturation vapor pressure, we can use the temperature in degree centigrade. Okay. So, you see that we have a small little expression in which we should be able to find out what will be the amount of precipitable water in a static atmospheric column. It is a useful exercise. There is a solved example given in the book. I do not think I will have time to take up any of the examples on this. So, but I suggest that you look at that example which is given in the book, all right, so that you understand how you can actually calculate, all right. All of these things can be automated in an Excel program or a computer program you can write. Okay. So, with that what we would like to do is we will move on, and we will move on to a slightly different kind of topic in which we will look at some more theoretical aspects. This was more practical. So, we will look at the formation of precipitation. Okay. So, we will start out with precipitation and introduce the concepts or the mechanisms that are required for the formation of precipitation. Okay. In this topic, we would look at different forms of precipitation, formation of precipitation, and then its measurement and data analysis. Okay. Okay. So, first thing we would look at is the formation. when we come to the formation of precipitation, I am sure all of you may have seen how the rainfall or precipitation is formed in the atmosphere. Okay. You have studied this in your 12th standard and earlier. You may have seen this in your undergraduate hydrology course. All right. We will just review it quickly. What are the two basic mechanisms that are required for the formation of rainfall in the atmosphere or in a cloud? There are two basic physical things that need to happen. Okay. Otherwise, you may have noticed that with the same climatic conditions, all right, same humidity, same temperature, same everything, all right, on 2 different days, one day it will rain, other day it will not rain. Okay. So, there is certain mechanisms that are needed or that are necessary for the formation of rainfall, condensation of the moisture that is there, water vapor in the atmosphere, and then it becomes heavy enough to fall. So, what are the two basic mechanisms? Okay. Well, first one is the lifting of an air mass. You have the moist air or air that contains moisture in the atmosphere. Somehow that has to lift, all right. As it lifts, the temperature goes down. As the temperature goes down, the water vapor condenses, all right. So, lifting of a moist air mass is one basic mechanism, all right. What is the other one? Well, we will come to that little later. So, first one is the air lifting or lifting of an air mass. Okay. Let me write it down. Requires the lifting of an air mass in the atmospheric or atmosphere rather I can say, so that it cools and some of its moisture condenses. Okay. So, for rainfall to form, the one basic mechanism is the lifting of the moist air mass. All right. Now, there are many ways in which an air mass can get lifted up. Okay. I am sure you may have seen there are different types of precipitation. All right. You may have heard about what is a frontal precipitation, what is an orographic precipitation, right, and what is a convective representation. They are associated or they correspond to different mechanisms of lifting of the air mass. All right. So, there are 3 basic mechanisms through which a moist air mass will get lifted up. What are those? Well, I just said them and we will just write it again. First one is what is called a frontal lifting of the air mass. What happens in a frontal lifting is there are 2 fronts, one is cold, other is warm, they are travelling against each other, all right, and when they come in contact, the warmer will get lifted up due to the frontal action. Okay. So, the warm air is lifted over the cooler air by what is called the frontal action. And the resulting precipitation is then known as the frontal precipitation. All right. We will not go into the details of this because we have already seen them. We are just looking at 3 different mechanisms. The second one, what happens in the hilly areas or the mountainous regions? How does the rainfall form there? Well, when the moist air is travelling, there is certain obstruction in the form of hills and mountains. All right. Due to that, the air rises. All right. That is called orographic lifting. In which what happens? The air mass rises to pass over a mountain range, and in that process it gets cooled. Okay. As the moisture goes up, the temperature goes down, it cools, and because of that lower temperatures the condensation takes place. and in the hilly areas we call that what is called the orographic precipitation, and the mechanism responsible is the orographic lifting due to mountains or barriers. Okay. The third one is what is called the convective lifting or convective precipitation. Okay. This is when the air mass is simply drawn upwards, okay, by convective action. Convective action. What is convective action? Well, just the difference of temperature in the height due to the difference in temperature, the temperature gradients set up the air gradients, and then the warm air gets lifted up. Okay. And the corresponding rainfall that occurs is called the convective precipitation. All right. So, this is as far as the one basic or required mechanism for formation of rainfall. What is the other one? We have seen that the lifting of the air mass is necessary, fine, but many times we know that we have same climatic conditions, same temperature, moisture is there, humidity is there in the atmosphere, pressures is same, all right. All other things are same, but one day it will rain, other days it does not rain. Okay. An important aspect, another important aspect for the condensation of moisture that is available in the atmosphere, we need to have a process which is called nucleation. Okay. What is nucleation? Nucleation is a process of condensation of water vapor in the atmosphere on very small tiny drops of some solid particles. It may be the dust particles, it may be some other things, small, these are called nuclei, okay, which help or which act as catalyst in condensation. All right. So, the next thing we would look at or say is nucleation. All right. What is nucleation? It is basically the condensation of vapor, water vapor on tiny, that is very small solid particles, which are also known as aerosols. Some of my atmospheric science friends, they call them aerosols or nuclei. Okay, is called nucleation. Okay. I would like to quickly look at these nuclei. What are those things? All right. These are basically some dust particles which are floating in the air. All right. These are particles which contain ions or which are ionized are more effective, okay, because they have the affinity to attract the water towards them. All right. There are certain ions due to various natural processes which are floating in the air, more effective due to the electrostatic force between them and water molecules or in the water. Okay. Then you have sulfur and nitrogen compounds resulting from combustion. Okay. Due to various industrial activity, we have lot of these pollutants floating in the air. I think I will write more and speak less. So, you have size of these nuclei are very small, of the order of 10 to the power minus 3 to 10 micrometers. Okay. And you know that what is the size of an atom? It is approximately 10 to the power 4 micrometer. All right. So, you can see that only a few hundred atoms can combine and make nuclei, which are very tiny small particles. I think I would like to stop at this point of time, wherein we have looked at the solved example, some examples of the calculation of various properties of water vapor. Then we have come and looked at how the rainfall is formed. There are two basic mechanisms, one is the lifting of the air mass and other is the nucleation, and then we have looked at a few properties or some concepts about the nucleation. In the next class, we would actually look at how the rainfall is formed in a cloud, okay, and then we will go on to the different forms of precipitation.